In this session, we are going to look at the relation between the electric field intensity, which is also sometimes in the shorthand written as electric field, and also electric potential. So, just before diving deep into this, let's have a quick recap of what all we have learned in electrostatics so far. The situation that we are dealing with is this. Let's say we have a combination of charges. Let's say here we have a Q1, a Q2, and let's say we have n charges kept here like this, and all of them are stationary. So whenever you keep them in any particular location, they start to modify the space around them. We call this modification or the field of influence as electric field. Then for an electric field at any particular point, you can describe it using two particular quantities. Let's say I'll just draw the coordinate system also. Let's say I have this XY coordinate system with me, and I have this particular point called A. For this point A, I can describe the field that has been created due to these charge configurations as an electric field intensity. Now sometimes the electric field intensity itself in the shorthand notation is called electric field. So I would suggest that you don't get confused because of that shorthand and be comfortable with this interchanging of the names. It's also called electric field. For this point, we can also define a scalar quantity, which is V, and this is electric potential. So electric field intensity or electric field is a vector quantity that describes the same effect of these charge configurations, and V, the electric potential, is a scalar quantity which is also used to describe this configuration. Then we also learned how to draw electric field lines, but for now these are the two major concepts that we will be dealing with. And then we looked at the concept of potential energy of a system of stationary charges. What we specifically said was, let's say this is the configuration and we introduce another charge. Let's say we have a charge Q that has reached this point A. It started from another point. We will call this as a reference point P. I can take it in the origin or somewhere. Right now I'm not drawing this diagram specifically, it's just to convey this idea. Let's say I have a reference point P and this charge Q started from here and it reached this particular point at A. So in this particular movement, in the influence of the electric field, what we can say is, we can define this quantity called the change in potential energy. The change, if I denote potential energy as U, then change in potential energy becomes del U. It is also equal to the final position's potential energy minus the initial position's potential energy. So this is what we can define. And this quantity, we defined or use this convention that this particular quantity will be denoted as the negative of the work done by the internal electrostatic forces of the system. So Q1 will apply some force, Q2 will apply some force, so on. All the charges will apply some force on capital Q, and all these forces will eventually do some work in this displacement of Q from point P, which is the reference point, to the point A, about which we are interested in calculating the electric field as well as the potential right now. So what we can write here is UA minus UB is equal to minus work done by the electrostatic forces in moving the point charge Q from P to A. Then we also use this reasoning that let us assume that in this movement there is no increase in kinetic energy of the system. None of the particles has gained any sort of speed. So under this assumption we can say that because only if the charges were acting on it, then there would have been some resultant force resulting in a resultant acceleration which would have increased the speed or kinetic energy, right? So there must be some external force acting on the system, and that external agent, essentially what it is doing is, it is ensuring that there is no kinetic energy, in the sense that the total electrostatic forces due to all these charges is balanced out by that external force. It's just acting in the opposite direction. So under those assumptions that the kinetic energy of the system doesn't change, we can say that because the external force always acts in the opposite direction to the electrostatic or internal forces, then the work done by the external agents in that particular assumption would be minus of the work done by the electrostatic forces, right? The only difference, the magnitude is the same, the only difference is in the direction, and the direction is just opposite. So I can write this as also work done by the external force in moving this under the assumption that change in kinetic energy is zero. So this is the big assumption about when we can use this formula to denote the change in potential energy. Once we had decided that, so this is our change in potential energy, what we said was we can also define other quantities about these points. Let's call these quantities as potentials of these points. Then we said that change in potential, let's say I denote potential as V, then delta V equals VA minus VP. I've used a B here, it should actually be a P because our point started from P and there's no point B here. So I'll just make this correction here. This is UP and this is VA minus VP, all correct. We define this quantity by convention to be equal to the change in potential energy that has taken place upon per unit charge. So I have this formula for V, it becomes equal to delta U upon Q. So this is the expression for change in potential. So I'll repeat this. The change in potential or the potential difference when a point starts moving from point P to A, this charge, capital Q, then this particular quantity is given as the total change in potential energy that has taken place upon the magnitude of the charge itself. So we will define or divide the change in potential energy with the magnitude of the charge to get the potential difference. So we've seen these formulae and then we said that by convention, let's assume that the reference point from which this particular charge has started moving, if we assume that the potential energy of the charge is zero and also this potential at that point is zero, then we arrive at this conclusion or the concept of the absolute potential energy at any point. So from this formula, I can say that the absolute potential energy will become equal to UA in this particular case, and similarly, the absolute potential from this assumption can be given from VA. VA simply becomes equal to the absolute potential energy, which is UA, and we divide it by the magnitude of the charge that is being transferred. So we have this expression for the absolute potential at point A. So after having gone through all these relations, now we are in the position to move a step forward. What we will do is find out the relation between the electric field itself and the electric potential. We can see that both of them are trying to explain this field of influence due to the charge distribution, and hence there must be some relation between them. So let's formalize the situation even further. We will use this situation and make some modifications here. Let's say I define this point B, and let's say we have this as the origin such that O, B and A all are collinear points, and then I say that OB, I'll call it as a position vector OB as R1 and position vector till OA is R2. So I'll write here, I can write this like this, OA is R2. Then I say that this charge itself, which is capital Q, it has started moving from point B and reached point A. In this particular motion, let's try to write the expression for the negative of the work done by the electrostatic forces. So what I will say is, let's say in this particular motion, there is an instance where this point has reached this particular position. Let's say this is point C, such that OC vector for us is vector R. So we are kind of depicting a general position. And then let's say that at this instant, what happens is, due to the forces acting on it, the electrostatic forces, they are doing some work, and as a result of that work, there is a displacement in this direction itself. We will call this displacement vector as dr vector. we will use this notation to denote that a small displacement has happened at this particular instance when the point reached at a general position of r. So what we can say is, because the charge is capital Q which is moving from point B to A, and we know the electric field intensity is E, we can say that the electric field intensity times the charge is the magnitude of force, right? So I can write F electrostatic is equal to Q times E. Now even E will be a variable here, it might depend on R, but I could write it like this also. Let's do that in fact. So E is a function of R in some way. So this is the expression for the force, and then I have the displacement also. So I can say that if this is the force, then the work done by the electrostatic forces. Right now only a small work has been done, so I will use a dW to denote that a very small work has been done in this very small displacement. So dW electrostatic is given as the electrostatic force itself dot dr. This is the definition of work done, right? So if I expand this equation, I will get Q E, which is a function of R, dot dr vector itself. And what I want right now is, let's calculate minus work electrostatic, because then I can replace that particular thing by saying that it is also the change in potential energy that has happened. So I can write du, or the small change in potential energy that has happened as a result of this small displacement. This is equal to minus dw elec ELEC, and then I'll put a minus sign here also. So this is the relation I get, and then I can say, let's take this into picture, the change in potential or the potential difference. Due to this potential energy difference, there will be a potential difference also, and it will be represented as, let's call it dV. Then dV is simply nothing but du upon q. We've seen this formula, right? That's right here, delta u upon q. And then in the most simplistic notation, I can write it as minus q E dot dr, and then I have to divide this by q, right? So I can cancel out these q's, and what I will get is the change in potential due to this small differential displacement is given as dV equals minus E dot dr. Now this is a very important relation. This is kind of the first thread into how can we relate the potential and the electric field. You can see here, we will highlight this equation, and then what we will do is, we will try to interpret it in certain different ways so that we can know more and more things about this particular relation. So the first way in which we can interpret is, I will write first interpretation here. It could be simply this particular formula. Let's say we want to find out the total potential difference in moving from point B to A. So what I have to find out is VA minus VB. From now on, we will also use another shorthand for this particular term. I will call it VAB. You can see that the way we have described this situation, this particular quantity VAB, or the potential difference between points A and B, it should be integration of dV. And then integration of dV is simply nothing but minus E dot dr. E is also a function of R. I'm writing it, I'm ignoring that fact here, because in this way the notation is pretty simple, right? You have to remember that it is in fact E of R, meaning E is a function of R. And here we can put limits like, it has started moving from point B, so the downward limit will be point B, and it will reach point A. So the final limit is that of point A. So this is the first important interpretation of this result. This interpretation says that if we want to find out the potential difference between 2 points, and if we know what is the electric field intensities distribution over this entire region, what we can simply do is VAB can be found out as an integration of minus of E dot dr over the limits, where initial limit is the initial point and the final limit is the final point's position. But this was the first interpretation of this formula. The second interpretation could be, let's say we have been given E and this particular vector dr in terms of vectors, as in we have vector components. For example, if we have been told that E is Ex I cap plus Eyj cap plus Ez k cap. And similarly, this differential displacement dr, if this has been given to us as, let's say, dx I cap plus dyj cap plus dz k cap. Then let's see how this formula looks like. Then dv becomes equal to, dv is a scalar, right, because we have a dot product here. dv, or the small change in potential and moving from point for this differential displacement, it becomes equal to, we know the form of calculating the dot product whenever we have been given components. What we will simply write is Ex dx plus Ey dy plus Ez dz. All the I caps, j caps and k caps, they vanish when we write dot product, and we simply have a sum of all these quantities. It's a scalar sum. So this is how we can write the expression for the small potential drop. So the thing that I'm getting at is, right now let's assume that there is displacement only in x direction and displacements in y directions and z directions are 0. In that particular assumption, this formula becomes equal to dv equals Ex dx. Another way of writing this is that if you want to find out the electric field's component in the x direction, you can say, oh, I forgot to put a minus sign here, dv is minus E dot dr. So this expression also becomes minus Ex dx. Make this small correction here. And then if we do this correction, we have the expression for Ex. Ex becomes equal to minus of delta V upon delta x. Now you have to notice this transition from in the symbols. We were using dv and dx earlier, and now I'm saying if I want to express minus Ex, or rather Ex, I can write it as minus of delta V by delta x. So there is this special significance of these symbols, delta V and delta x. It means that we are assuming that there is displacement only in x direction, and we are assuming that there is no displacement in y and z directions. Just like this is called derivative, where we assume that the displacement is in any general direction. I can write this or this as derivative. This is called partial derivative, wherein we fix two mutually perpendicular directions and study displacement in only one of the other perpendicular directions. This is called partial derivative. So this is also an important interpretation of this particular relation that is kept here. So we can similarly write, if I want to find only the y component of the electric field, or the component in the y-axis, I can simply write it as minus delta V upon delta y. And similarly, Ez becomes equal to minus delta V upon delta z. So we finished two interpretations. Now let's look at the third interpretation of this equation. For this, let's redraw the situation from another perspective, and this perspective is, let's say in this particular diagram only, E is in this direction and our dr is in this direction. This is dr, this is E. Then dv is what? dv is E dot dr with a minus sign. So it becomes equal to, if we solve this, or rather expand the dot products convention, we get E dr cos theta, where theta is the angle between E and dr. So now you see this interesting thing, that this vector E can be resolved in two directions. One direction is perpendicular to that of dr. This component is E sin theta, and the other component is in the direction of dr itself. Let's say it is E cos theta. And then if you look at this formula, you can interpret it, if we rearrange these terms, we have a minus of E cos theta, and then we have a dr. Had we only had this sin theta component, or rather if we had this particular fact that the electric field's intensity is perpendicular to the displacement, then this formula would have become E dr cos 90, because theta would have been 90 degrees then, which would have meant that there is no change in the potential if we move along this direction dr, which is perpendicular to the direction of electric field intensity. So this is one of the important aspects about the potential difference, that whenever we move in the direction of electric field, there is a potential difference. But if we move in the direction perpendicular to the electric field, then the potential difference is zero. So this was the third very important thing about the relation between potential and the electric field itself. So on the basis of this concept, I will repeat this concept again. It says that if we move in the direction of electric field, there is some potential difference. It is given by this formula. dV is minus E, and the E cos theta means that the component is in the direction of displacement, times dr. However, if we move in the direction perpendicular, there is no potential difference. On the basis of this conclusion, we can draw this concept of equipotential surfaces. Just like we have electric field lines, which in a way depict graphically how the electric field intensity would look like. They say that if you want to draw a tangent to those electric field lines, we will get the direction of electric field at that point. Similarly, we can draw electric potential as something very closely related to electric field lines. For example, if we have a charge particle kept here, let's say this is charge Q, then the electric field lines, if this is a positive charge, it looks like this. Notice this is a three-dimensional figure. Now, what I can do is, I can take a sphere around this charge such that the charge is kept at the center of that sphere. Let's denote this sphere like this. In the screen, it will look like a circle. So for this sphere, we notice that because the electric field lines are radial, the electric field lines always make an angle of 90 degree at any point they intersect with the sphere. It means that all the potential difference that will happen due to this particular electric field, it will happen in the direction of electric field lines, and at any point, if you move from this point in the sphere to this particular point, there is going to be no potential difference at all, because if you move along the sphere, this point is at the same potential, this point is at the same potential, this point is at the same potential, and so is every other point in this particular surface. So this is the concept of equipotential surfaces. So one way of depicting an electric field is the electric field lines. The other way of depicting an electric field are the equipotential surfaces. We could draw this surface, or we could take some other r, let's say this was r1 as the radius of the sphere. We could have drawn another surface at r2, where r2 was the radius of the sphere. Again, the center would be this location of the charge itself. But if you consider this bigger sphere, even for this sphere, if you took this point or this point, it doesn't matter. Potential is same at any of these points. However, the potential at this point and the potential at this point, they will differ because they are not part of the same equipotential surfaces. So this was an important concept of equipotential surfaces, and you saw that it directly emerges from this particular relation. The change in potential is given as minus E dot dr. I would like to summarize. What we did here was, we started with these concepts of the potential energy and potential itself, and then we tried to find out the relation between the electric field and potential. We found this particular relation. It relates the change in potential with the change in displacement in the electric field intensity. And then what we did was, we tried to interpret this equation in three ways. The first way led us to this concept that if you want to find out the potential difference between 2 points that are located differently from each other, then that will be given by this expression minus E dot dr. You have to integrate it. Then the second interpretation was, let's say you have been given the potential at any point and its variation with x, y and z coordinates, then you can find out only on the basis of that information that what is the electric field in the x direction or y direction or z direction. You will use these relations for that. And then the third interpretation was related to equipotential surfaces, where we interpreted this equation only in this way, that if we have a component of electric field which is perpendicular to the direction of displacement, then there is no potential change in that direction. However, if the electric field is parallel to the displacement, then there is potential difference. So this particular thing was used to graphically represent electric field with the help of equipotential surfaces.